In DeFi today, a large amount of capital flows through vaults. Vaults have become ubiquitous across the ecosystem. Protocols like yield aggregator, lending platforms, and asset managers rely on them to manage user funds and generate yield. But early on, every vault implementation worked differently. Each protocol had its own interface, its own accounting logic, and its own way of calculating deposits and withdrawals. Now, this made integration difficult and slowed down composability across the ecosystem. ERC4626 was introduced to solve this. It defines a standard interface for tokenized vaults, making them easier to integrate, test, and compose. In this course, we'll cover why vaults, what problem existed, and how vaults are solving it. Then we'll touch on the definition of vaults, tokenized vault standard, explaining ERC4626. Then move on to the technical specifications, the reference implementation, focusing on Open Zeppelin and Solidity. Then we'll touch on the security consideration with a focus on inflation attack, the mitigation strategies for inflation attack, then testing the vault, and lastly, X16Z ERC4626 test suite. To understand ERC4626, we first need to understand why vault exists in the first place. In DeFi, users often want to deposit assets into strategies that generate yield. Examples include lending assets on money markets, providing liquidity, or running automated strategies. Instead of requiring users to manage these strategies manually, protocols introduced vaults. Now, a vault is a smart contract that first accepts users' deposits, allocates those assets into yield strategies, and then track each user's proportional ownership of the vault. However, before ERC4626, there was no standard way to implement vaults. Every protocol implemented its own logic for deposits, withdrawals, and various accounting methods. This meant integrators had to write custom adapter codes or integrations for each vault, which made DeFi less composable. ERC4626 standardizes this interface, similar to how ERC20 standardized fungible tokens. A vault is a coordination interface for on-chain capital allocation. It is a programmatic, non-custodial setup that enables on-chain asset management through smart contracts. Simply put, a vault is a smart contract where users deposit their tokens like USDT, USDC, or even DAI and receive shares in return. Now, these shares represent a proportional claim on the vault's asset and any generated yield. The vault deploys deposited funds into predefined yield-bearing strategies, and users can later redeem their shares to withdraw their initial deposit plus accrued returns. Now, conceptually, a vault serves a role similar to a traditional savings account or fund manager, other than it is implemented on chain. Now, execution is transparent, non custodial, and automated, removing the need for intermediaries while enabling composability across the DeFi ecosystem. What is the tokenized vault standard? ERC4626 defines a standard API for tokenized vaults that represent shares of a single underlying ERC20 token. It extends the ERC20 standard, meaning vault shares themselves are ERC20 tokens. Now, this allows vault shares to integrate easily across DeFi. The standard defines how vaults should accept deposits, mint shares, process withdrawals, convert between asset and shares, and expose other accounting methods. Now, by following this interface, vault implementation becomes predictable, composable, and easier to integrate with other protocols. ERC4626 introduces a set of core functions that every compliant vault must implement. These functions can be grouped based on their role in the vault. Let's take a closer look at these functions and how they work in practice. The first group is the assets and share flow functions, which has the following methods. The deposit function, which allows the user to deposit assets into the vault and receive the shares in return. The mint function, which allows a user to mint a specific number of shares by depositing the required amount of assets. The withdraw function, which allows a user to withdraw a specific amount of assets by burning the corresponding shares. The redeem function, which allows the user to redeem a specific number of shares for the underlying asset. Moving on, let's talk about the other category, which is the preview function category. Before executing any state changing operations, users and integrators often want to simulate the outcome. So, ERC4626 provides preview functions for those purposes. As such, users and integrators can preview deposits, preview mint, preview withdraw, preview redeem at the current block given the current on-chain conditions. Now, this function returns expected results without modifying the state. They are especially useful for front ends, aggregators, and integration that need the exact values before submitting transactions. The next group is the limit function category. This group defines the operational boundaries for users. The functions here include max deposit, max mint, max withdraw, max redeem. These functions specify the maximum amount a user can deposit, mint, withdraw, and redeem at any given time. Now, they are useful for enforcing constraints such as liquidity availability, withdrawal limits, or even other protocol specific restrictions, right? The final group focuses on accounting and value conversion within the vault. The function includes asset function, which returns the address of the underlying asset managed by the vault. The total asset function, which returns the total amount of assets currently managed by the vault. Convert to shares function, which converts a given amount of assets into the equivalent number of shares. And lastly, the convert to assets function. This converts a given number of shares into the corresponding amount of assets. Now, all this function put together allows the implementation of a standard API for tokenized vaults. Now that we have walked through the core functions defined by ERC4626, let's take a step back and look at the standard itself. So now the first thing we want to do is to head over to the Ethereum Magician website, where the standard was first proposed by Joe Santoro in 2022, right? Now, this website actually has all of what the proposal entails and then some contributions from other major protocol developers. Fast forward to the finalization of the standard. Now we have the standard here, just like what we explained earlier on, right? The standard allows for the implementation of a standard API for tokenized vaults, right? And in any case, the reason is because there was like lack of standardization for vaults, and there was various implementation, for different use cases from lending markets to aggregators, and also intrinsically interest bearing token. Now, in any case, to make integration with this diverse implementation required that each integrator had to build their own custom, adapters, which are sometimes prone to error and also waste development resources. Now, this is where ERC4626 comes in, right, to lower the integration efforts for yield bearing vaults. Now, let's take a look at the various methods, just like we've explained previously. We have the asset function, which returns the address of the token that the vault manages at the time. And then we have the total asset function, which returns the total amount of the underlying assets managed by the vault. Then other functions such as convert to shares, which basically takes in the assets and then returns the shares, right? Just like we mentioned in the previous explanation, how that the convert to shares function basically exchanges your assets to shares, right? Also, the same thing applies to convert to assets, other than it is the reverse, right? Now, the same explanation goes for the rest of the functions, just like we've earlier explained in the previous session. And so the events available in the ERC4626 standard includes the deposit event and also the withdraw event, just to mention. Okay, so in the next session, we're going to be talking about the various reference implementation. After understanding the ERC4626 interface, function, and events, it is useful to examine existing reference implementation. Now, the two widely adopted implementation are provided by OpenZeppelin and Solidi, right? Both offer compliance-based contracts that implement the ERC4626 standard while allowing developers to customize vault behavior through overrides and hooks. Now, let's get right into it by, taking a look at the first one, which is the Open Zeppelin implementation. As you can see, this has multiple imports. Imports ERC20 because the vault share is an extension of ERC20, and also it has the ERC4626 interface and then some other imports needed for the implementation. And now over to the contract, we can see various variables and then error declared. But most importantly, I'll be going into like the major parts here, which is like first the constructor. As you can see, it takes in the assets that the vault will be managing. It could be like an already deployed contract, in this case USDC or DAI, or for testing purposes, right, you could just deploy a new ERC20 contract and then pass it here. Then we have some major functions as defined by the specification. total assets convert to shares. So I'm going to be dwelling here for the most part how like the asset to share conversion rate is being calculated, because this is like the most important part. And so one of the things to understand is that the assets to share exchange rate is majorly dependent on the total assets and total supply. Now, total assets in this case is the total amount of assets being managed by the vault at the time, and then total supply is the total number of shares already minted by the vault. Now, in any case, this relationship has to be, one-on-one, right, for the most part, for the asset to share exchange rate to be, one-on-one also. So yeah, I'm gonna be touching on like the convert to shares. Let's just get into it and see how this works. Okay, so let's take a look at the formula for the um, convert to shares, right? Convert to shares. So to get the formula, we're going to say shares received, equals the assets deposited multiplied by the total supply, right? Then divided by total assets. Okay, so now with this formula, we're going to be getting the amount of shares to be received when we deposit an asset. Now, this is how like the shares or the convert to shares function works under the hood. Now, it's important to know that one of the specifications that ERC4626 specified was the fact that convert to shares sort of like rounds down to zero, right? And in any case, this is basically like the formula. Now let's take a practical example. So just to mention, right, I'm going to be talking about quite a number of things, right, from inflation attack and how this function sort of like prevents, inflation attack later on with virtual shares. But in any case, what we need to note here is how like the shares received are initially being calculated before all of the advent of like inflation attack and whatnot. Now, before then, in the case where total supply equals to zero, right, the function sort of like says that, oh, then the shares minted should equals to the assets that the user says he wants to, mint, right? If total supply equals zero, now at this case, then share equals the assets, right? And so if you take a look at this initial formula, that means that if a 1 minute. So if a user says he wants to deposit one asset, right, that means that the shares received will be what? In this case, one, right? This is at the point where like the total supply is equals to zero, right? So if a user deposits one asset, they get, one shares back by any chance. So that makes a lot of sense because the assets and also the share now maintain one-on-one or one-to-one relationship, right? And there's no discrepancy. Now, if we have like a subsequent deposits, right? So let's take for instance, we have a subsequent deposit, right? Then it then takes this formula, right? Where like, take for instance, I want to deposit 5, right? So that would be 5 times current total supply is what? Total supply is 1. That's 5 times 1. And then total asset is also what? 1. That would be 5 divided by 1 equals 5. That means that one asset represents 1 shares. And because I am bringing 5 assets, I am getting 5 shares in return, right? Pretty much the formula, right? I hope that explains like the first part. Now, one of the other things to note is that this formula is prone to like inflation attack, right? Now, inflation attack is a scenario where like the assets and share relationship is distorted. Usually, when an asset is deposited, shares are being minted back in return. But what if there's a scenario where like an attacker can, send an asset directly to the vault without the total supply increasing? Now that means there's going to be a distortion. So now let's take a practical example of like the inflation attack scenario. Now, on like a one-to-one type of vault, right? An attacker deposits one asset and gets, one shares in return. Now, because this is sort of like vulnerable to like inflation attack, right? Now the next user sort of like wants to deposit, let's say, um 99 assets, right? And then the attacker already has like one share in the contract, right? Now, in a typical inflation attack scenario, right, the attacker sees this user's deposits in the mempool and sort of like front runs the user. First, what he needs to do first is to, send like 100 assets to the vault. Now, let's say attacker sends 100 assets, right? 100 assets to the vault. Okay, so what then happens when the attacker sends 100 assets is that, they are not calling deposits directly. They are just sending it to the vault contract address. And because they are doing this, the total supply will not increase. That means the shares minted will not increase, only the assets. Now, what happens here is we're going to be having the assets deposited for the user. This happened because the attacker already sort of like front run the user, right? And then the total assets has increased, but total supply is still the same. So what will then happen is that the 99 assets to be deposited will be 99 times total supply, which is still like 1, and then that's 99 divided by total assets, which is like 100. And so when we do the division, we're going to get something like 0.9 whatever. And so this is going to like, because like I mentioned, right, convert to share sort of like rounds down, right? So if we do 99 times total supply, which is 1 at the moment, divided by 100, right? So we're going to have something like 0.9 999. And so this basically rounds down to 0 for the user. So because the vault sort of like maintains one-to-one relationship before like the donation, and what happens here is that the user no longer would have 99 shares but now have 0 shares. And so that way the attacker holds all of the vault assets, right? Because they initially have 1 shares in the contract. And so that means with that in their control, they'll be able to take both the 100 assets and the 99 asset deposited all to themselves, right? Now, so what is the solution to this, right? So this is where like Open Zeppelin comes in, where like there is, so let's take a look at this function over here, right? And so the convert to share function in Open Zeppelin from like version 4.9 and above sort of like takes into consideration virtual shares, right? Now, what virtual shares basically does is that it adds like an additional share to like the total supply and also like a constant figure to the total asset. Now, this is basically the same thing that we mentioned in over here, right? Other than the fact that we now have a decimal offset. Now, this decimal offset is basically like the additional virtual shares added. And so I'm still going to be explaining this part. So with this added, it means that inflation attacks become economically unprofitable for attackers. I'm still going to like sort of like get there in a bit. But yeah, what happens here? So let me just copy this guy so I can explain in detail. So now, this is basically what we have now. So we have assets multiplied by total supply plus 10 raised to the power decimal offset. Now, if we take a look at Open Zeppelin, the decimal offset is currently like 0, right? You can always override this to whatever decimal offset, whether 3 or like 6 or 9. And so, moving back here, what happens here is that because our decimal offset is 0, so 10 raised to the power 0 becomes 1. So we'll be able to add 1 to the total supply and also add 1 to the total assets, which is basically like the concept of, the virtual share thing. So now, in any case, what does this mean? Let's take a look at the case of like an empty vault or like a near empty vault. Now, so if a user wants to sort of like deposit initially, now we don't need to use like this function or like this calculation anymore, where like if total supply is equals 0, then the share equals like the asset to be deposited. Now, instead of that, by default, right, the function or the vault maintains like a one-to-one relationship by default. Now, how do I mean? So let's take, for instance, a user wants to deposit one, right, one asset for like a new, for a near empty vault or a new vault. So that would be one. Then total supply at the time is zero, right? Zero plus one equals one. And then total asset two is zero plus one, that's one. So we have one times one, right, divided by one, which basically maintains like the one-on-one relationship. And this rounding is basically like the parameter for either rounding up or rounding down. And we basically know that convert to shares rounds down, right? So pretty much this sort of like checks out, right, for like for an empty vault or like a near empty vault. Now let's now take a scenario for how it sort of like prevents inflation attack, right? Now let's say we have like a scenario where there's like a one-to-one relationship, right, already. An attacker already deposited like one asset and gotten one share in return, and then the user wants to like deposit say like 99. User wants to deposit 99 say USDT, right? So what happens here is that now the attacker sort of like saw this in the mempool and sort of like inflated or donated, assets to the vault contract. Now in this case, what happens is that the attacker sends, let's say, 100, right? Now this is without calling the deposit. He just sends it to the, to the vault contract, and this sort of like distorts the one-to-one asset to share relationship. Sends 100 USDT, right? And oh sorry, attacker sends 100 USDT, right? And pretty much it. Now what we would have now is a scenario of, say, when the user 99 USDT want to be deposited, we have 99, then total supply at the time will be 1 plus 1, because 10 raised to the power 0 is 1. And then at the time also, total assets is going to be 100 plus 1, right? Pretty much. So now we have 99 times 2, which is going to be like 198, then divided by 101. So we're gonna be having a figure around 1.98. I mean, at the end of the day, the user goes home with like one shares, right? And so pretty much, and so what happens here is the fact that now we have like three shares in the contract, one to the user, one to the attacker, and also one to like the virtual shares. Now if the attacker wants to claim their money, in this case they'll be able to claim like 67 USDT, because a part of a part of it has gone to like the virtual shares, right? And so in that case, it becomes like economically unprofitable for like an attacker to just want to lose money. And sometimes, depending on like the offset, right, the amount to lose is usually higher, right, and it becomes like unprofitable. And so this basically just steers off like attacker by any chance to even like distort the original one-to-one relationship. And so this is like the concept of how we can prevent, inflation attack using the virtual shares implementation from Open Zeppelin, right? Pretty much it. I think the same thing holds for like convert to asset, the same analogy that we've just explained. And yeah, let's move on to the second, implementation, which is by Solidi, right? Or one of the major good part about Solidi is that it is gas optimized, right? Pretty much. So it has the same functions that have been spelled out by the standard, right? Other than the fact that it is like gas optimized, right? As you can see, it has some like assembly code, right? Other than that, it also has like the functionality to like toggle between if to use virtual shares or not to use virtual shares, right? I mean, this is like sort of like inspired by Open Zeppelin also, but the fact that you can toggle the use of virtual shares. And so if you're not using virtual shares, it basically like uses the normal formula, right? And if you turn on virtual shares, it basically just adds, an offset to both the total supply and also like the constant to like the total assets in this case, right? Pretty much. And the same thing applies to convert to asset, and the same like logic stands. One of the things I also want to mention for the Solid implementation is the existence of hooks, right? And so we have the before withdraw hook and also like after deposit hook. Now, this is so fascinating because you can basically do stuff after deposit. And so take for instance, when a user deposits, after the deposit is executed, you can basically, forward the deposits to like a particular strategy where it's earning yield. So I'm going to be talking more about that in like the hands-on session. But in any case, that's pretty much like the essence of a hook. So this hook is called after any deposit or mint. And then we also have the before withdraw hook, which basically is like a type of hook that is called before the withdraw. Now, a practical example of that is, say you want to withdraw the earnings from the strategy that you already deployed to. So the earnings are withdrawn from like the strategy, and then it's now available in the vault, and then the user can, withdraw that yield. So pretty much what I want to share about the different reference implementation, we've taken a look at Open Zeppelin, majorly like the core parts of how to convert to shares and also how it applies to convert to asset, and then the prevention for inflation attack, right? Using virtual liquidity or virtual shares, and then also the Solidity implementation, how that is gas optimized, right? And pretty much it. Before we go into the hands-on vault deployment, let's take a look at some important security considerations with a focus on inflation attacks. Understanding ERC4626 is not sufficient to build safe vaults. You also need to understand common pitfalls that can arise when implementing vault logic. Some of this includes reentrancy attack, fee on transfer or rebasing tokens, oracle manipulation, rounding drift, and also first depositor inflation. Now, in this course, we'll focus on one key issue, which is the inflation attack. This primarily affects new or near empty vaults. What then is an inflation attack? An inflation attack exploits how ERC4626 vaults calculates the exchange rate between assets and shares, especially when the vault has low or no liquidity. At a high level, the attacker manipulates the assets to share ratio so that future depositors receive significantly fewer shares or even zero shares, while the attacker retains full control of the vault. Now, this happens because ERC4626 rely on the ratio of total asset to total supply. If this ratio is distorted, the share calculation becomes inaccurate. One key way this distortion occurs is when assets are transferred directly into the vault without minting corresponding shares. Now, this creates an imbalance between total assets and total shares, which the attacker can then exploit. This vulnerability is most severe when the vault is new and with low liquidity. Now let's walk through a practical example of inflation attack in practice. Alright, so what I want to do is to go over the inflation attack in practice. And to do that, I've built like a vulnerable vault and also a token contract, which is going to be managed by this vault. Now let's have a look at this. This vault basically has like a constructor that takes in the asset to be managed by the vault, the name and symbol of the vault shares, the total assets, which returns the balance of the asset managed by the vault, and also this deposit function, which is overriding. And then this vault basically uses the soulmate implementation. And yes, let's take a look at this deposit function. It requires that assets should be greater than zero. If not, it throws an error, zero asset. And so this basically, uses the function preview deposit, which basically returns the shares. Right now, let's have a look at what this preview deposit looks like in the contract, right? So when we have a look at preview deposits, it basically uses the convert to shares function, which is the function that manages asset to shares exchange ratio, right? If we have a look at the convert to shares, it basically says it loads the total supply to a local variable, and then it uses this formula to return the shares to the function or the user. And then it says that if supply equals zero, meaning that at the point where the vault is still at the initial stage, when total supply is zero, it means that no shares has been minted, and this is the very first stage of the vault. And so if supply is equals zero, it says that the shares to be minted to the user at the time, if a user is bringing one asset, then return the shares to them to be the same one asset. And then if the supply is not equal to zero, then you should use this formula that I earlier explained, right? So this is pretty much the function that handles the convert to share ratio, right? The same thing for convert to asset. And then this basically formulates the basis for the inflation attack, which I'm still going to like explain, in this video. Now let's deploy each of these contracts and then see how it works in practice. Now the first contract I'm going to be deploying is the token contract. It's an ERC20 token. It has a name build and also symbol BUIDL, right? So let me deploy this contract by going over to the deploy and run transaction tab. So we're going to be using 3 accounts here: Alex, which would stand as the attacker; Bob, the user; and deployer, the account to deploy all of the contracts. And so now we'll pass in the deployer address here and the initial owner, and then deploy, and hence our contract has been deployed, right? And so we have all of the functions over here. The next thing we want to do is to mint this asset to each of the users, right? So I'm going to be copying Alex account and then I'm going to be minting to Alex, right? And so let us mint the sum of 500 build tokens to Alex, right? I'll do the same for Bob, right? And then transact. Now let me take a look at each of their balance. Let me check for Alex and then also check for Bob. So now we have each of the assets available in each user's account. So that's the first step. The second step is to deploy the vault contracts, right? And then to do that, we're going to be loading the vault contracts into the deploy and run transaction tab, and then passing the asset contract, which is to be managed by the vault, right? And the name is going to be simple vault, right? And the symbol is SV, which is the vault shares. And so I'm going to click on deploy, and now as you can see, our vault contract has been deployed. It has all of the specifications from the standard, and we are good to go. And so what I want to do now is to approve the vault contract to be able to spend on behalf of each of the user, right? And so to do that, I'm going to go into my token contract and load the approve function. So I'm going to pass in the vault contract here as the spender. I'm going to switch this account to Alex, and then the value should be 100 build tokens, right? Or let's say 100, right? And then I'm going to be switching to Bob also, same contract. And then so we've approved the vault contract to spend each of the users token. Now in this case, let us remember that Alex is going to be the attacker, right? And then Bob is the user, right? Now to reiterate, the concept of inflation attack basically happens when the assets to share ratio has been distorted, right? And in any case, this means that total supply did not increase, but total assets increased. Now this will happen when there is a donation into the vault contract. But in any case, that's like the concept of inflation attack, where there is a donation into the vault contract, but the corresponding shares are not being minted, which then distorts the asset to share relationship, right? And so this is what we're going to be doing here. Now that we've deployed the token contract and also the vault contract, now let's simulate this. Now the first thing is that the attacker, which is Alex, right, would have to own like one share in the vault, right? The next thing is Bob. Bob would have to deposit some assets, right, which is the build token asset, and then the attacker siphons the funds, right? sorry, takes the money. So let's see this in practice, right? Um, so for the attacker to be able to get one share, let's just directly use Mint, because Mint says how many shares do you want, and then it does the calculation under the hood. Let's say we want one share. Mind you, the total assets right now is 0, and total supply is also 0. So this means our vault is still early and initial, and then it basically just uses this calculation. It gives us whatever assets we are trying to deposit at the time. And so that's basically the concept. So now what we want to do is to, mint one shares, right? So the receiver in this case is going to be Alex, the attacker, and then we'll transact. Now, when we take a look at total assets and total supply, everything must have changed to 1, and then total supply also changes to 1. Now we deposited, or we said we needed one share, and the contract calculated how much that would require and took one asset from us, right? And so there is a one-to-one relationship occurring right here. Now the next part is to do the donation. Now in any case, Bob wants to deposit 100 build tokens into the contract, but the attacker sort of like saw this in the mempool, right? And then uh, front run Bob, right? So to front run Bob, we would have to transfer certain assets. You would have to transfer the assets from himself to the vault contract without calling the deposit function. So I'm gonna paste the vault contract and transfer the sum of 100 build tokens, right? And so now that this is done, we should now see that the total assets has increased, right, to this value. But total supply in any case still remains 1, because there was a donation instead of like a deposit that uses like that mints the corresponding shares to the user. Now that this has been done, now the Bob transaction will have to go through. Now let's change this to Bob and then try to call the deposit function, right? So this is deposit function, and the assets we want to deposit is 100 um, build tokens. The receiver is Bob, which is the user, and then we transact. Now, when we take a look at the total assets, it increases from this value to this value because now there's a new deposit, but total supply still remains the same as 1. Now this still remains 1 because when Bob did the transaction, inflation attack already occurred, which would then result to the shares of Bob rounding to 0, right? And so pretty much what happened in this case, why total supply did not increase. But right now, the attacker owns one share, right? So that means the attacker can take full control of everything in this vault. And so let's redeem one share and copy Alex address over here and then call transact, right? So this shows that the transaction went through. And then let's take a look at, total assets. Alex have been able to siphon all of the money in the contract, and also total supply is now 0. Now, when we take a look at the address of, or the balance of um, Alex in the asset managed contract, we will see that Alex now has 600 tokens. He initially had 500, but now he has 600, meaning it took all of Bob's money. So this is the concept of inflation attack. Basically exploits the early vault condition and how asset to share ratio have been calculated. Now in the next session, I'm going to be taking a look at how to mitigate this issue. All right, so in the last session, we talked about security consideration with a focus on inflation attack. In this session, I'm going to be talking about the different mitigation strategies for inflation attack. All right, so before we go into that, let us take a look at some of the ecosystem discussion around inflation attack, right? Now, if we head over to this page, we can see the various, discussion around inflation attack, how it has been prevalent, and some of the major ways to mitigate it. And so one of the members from Open Zeppelin team sort of like mentioned some of the mitigation, which includes using an ERC4626 router, keeping track of the total assets internally, creating dead shares. Now, some of the practices in production would be from MofoDAO, where they, at initialization, deposit some assets into the vault, which technically is more like creating dead shares. But in this case, it is to the vault address. Now, the other option is by yield box, right, which is basically adding virtual shares and virtual assets to, the vault, and which is what we've talked about, in all of this course where it has been implemented by Open Zeppelin, as we can see over here, right? Adding of virtual shares and also adding of virtual assets, same as the Solidity implementation, right? But in any case, let's take a look at this implementation or some of these mitigation strategies in more detail. Now, I'll head over to this article that I published some weeks back, right? So as we can see, some of the mitigation strategies for inflation attack includes using ERC4626 router. Now, each of these mitigation strategies has their pros and their cons, and we'll be going over that in this part. Now, using an ERC4626 router basically intermediates all user interaction with the vault. Now, that means that a router can enforce minimum share issuance, detect near zero share outcomes, block or revert suspicious deposits before they reach the vault. Now, so because the router sits between users and the vault, it provides a controlled execution environment where edge cases such as inflation attack can be mitigated at the integration layer. Now, this mitigation strategy also comes with its own con, where users must trust the router, of course, as an additional component, and the underlying vault remains vulnerable if accessed directly. Now, other than that, it's important to know that a practical example of this has been implemented by Yen Finance. Moving on, we also have the use of virtual shares, right? Now, this is the most widely used mitigation strategy, which, as we can see, was first introduced by Udebox and later adopted by Open Zeppelin. Now, this method works by introducing virtual liquidity into the asset share exchange rate. Now, this fixed virtual offset is added both to the total supply and the total asset. If we take a look at Open Zeppelin implementation, we'll see that he has this decimal offsets, which we can override. And now, the higher we want the inflation attack to become economically unprofitable, the higher we sort of like had the decimal offsets. Now, in this case, we said we should return 8, which initially would return 0. Right, so that means we've increased the tenacity rate of inflation attack becoming economically unprofitable. Now, this decimal offset is then used in the convert to share logic and also the convert to asset logic, right? In any case, this has both its pros and cons, right? Now, one of the cons is that a small portion of accrued value is captured by the virtual share. Now, in loss scenarios, exits are slightly asymmetric, and those that exit early experience marginally lower losses than later exiters. Now, the next part is creating dead shares, which also acts as a form of mitigation strategy, which in this part I put it as initial deposit pattern, right? Now, this basically says that you should mint dead shares during the vault's initialization. And what happens is that while you are initializing the vault, you mint an initial quantity of shares to a particular address, and most times this can be a non-recoverable address. This basically ensures that the vault never starts at 0 and reduces the profitability of inflation attacks. Now, MofoDAO took it further by doing the initial deposit pattern, right? In this case, they basically sent an initial share to the vault's contract address. Now, for this to happen, it requires that you pre-compute the vault address and grant its approval before deployment. So these are some of the ways of mitigating against inflation attack. I hope I've been able to do justice to that. To reiterate, we have the use of ERC4626 router, the use of virtual shares, which is the most commonly used approach. As we can see, this has been implemented in Open Zeppelin and also Solidity. And then lastly, creating dead shares. So we have come to the most interesting part of this course, where we're going to be building, deploying, and also testing our ERC4626 tokenized vaults, right? Now, in this session, we implement a single strategy ERC4626 vault that routes deposits into a single yield source. Now, we will bootstrap the project with Foundry, implement the vault using Solid's ERC4626 base contract, test on a forked mainnet state, validate the behavior using the A16Z ERC4626 test suite. Now, to get started, it's important to reiterate on the core of vaults. I'm going over the explanation. Now, a vault is a smart contract that accepts deposits, right? And then these deposits are being directed into various yield sources. For the most part, this yield source can be a single, strategy yield source or multi-strategy yield source. So for this course, we're going to be focusing on the single strategy vault, and in this case, our yield source is going to be Aave. And so we can treat this as an ERC4626 wrapper that deposits underlying assets into Aave, and then we get, the vault shares in return. So the next step is to set up our development environment. For a quick start, you can find the full code on GitHub over here by just clicking on the link, and it brings you to this link, and you can see the contract over here, right? So now the next step is to basically clone the contract, and then after cloning the contract, you can cd into the directory. Now that we have our contract cloned, let us cd into the directory and then open this up on VS Code, right? And so now our contract has been, initialized for us, and then the next part is to install all of the dependencies, right? By running forge build. As you can see, this contract has the lib folder, right? All of the dependencies, the A16Z property based test suite and the Solidity contract dependency. So wait for this to, deploy and then compile. So now that it has compiled, the next thing to do is basically do a quick walkthrough of this contract. I'm going to cancel this and reload this so the error goes away. Yeah, so let's walk through this contract. Like I mentioned, this is for educational purpose, right? We're going to be walking through how Evolve accepts deposits and how the deposits can be, directed to a yield source. And hence, we are calling this like an ERC4626 wrapper for Aave v2. So it has the various imports, the major ones: ERC20, ERC4626 base contract, the Aave mining interface, which basically helps us to claim the liquidity mining rewards, the lending pool interface, which basically helps us to supply and withdraw from Aave v2, right? And so let's go right into it. We have the Aave a token contract, which is given to us when we supply, assets on Aave, and then the underlying assets, which can be DAI in this case, then the Aave mining contract, the reward recipient contract, the lending pool. The constructor basically initializes all of these, variables as the case may be. Now, the claim rewards function helps us to claim the liquidity mining reward. Now, the other functions that I want to touch on includes the deposit function, which helps us deposit into the vault, and then after depositing, it then routes these deposits into the yield source, in this case, which is Aave. As you can see, all of the stated functions that the standard already specified are here: the asset function, the withdraw function, and the major ones, the redeem function, right? Total assets. But one of the major ones that I want to explain is the after deposit hook. Now, this hook basically is fired um, after deposit is done. As you can see, this function has been overridden. This means that the deposit itself exists in the base contracts, right? But what this after deposit hook does is that it approves the lending pool, and then we can directly deposit into Aave, and then the A tokens is given to this vault contract. I hope that makes sense, right? So this is like the essence of the hook, as we can see, or as I sort of like explained in the previous session. Now, every other function stands the same, and pretty much it's right. Now, that's the first part. So this is basically what I've just, iterated on. The contract that we just initialized is an ERC4626 compliant tokenized vault that wraps Aave v2 lending position. User deposits an underlying asset, for example, DAI. The vault supplies the to have a V2 to earn yield, and in return, the user receives vault shares that represent proportional ownership of the pooled position. Now everything stands the same, right? But like I already mentioned, we have the deposit hook in the contract, right, which is fired when deposit is done, right? Basically, um, runs after vault transfer assets from the user and means shares to the receiver. And it answers a simple question: what should the vault do with the assets after receiving them? Now, in this case, the vault supplies the assets to Aave V2. Now, one of the other interesting things about the implementation we have over here is that it uses virtual shares, right? As you can see, Solidity implementation helps you toggle on or off between using virtual shares. In our case, we've turned it on, and so we'll be using, the decimal offset also. Um, if you want your inflation attack to be mitigated and want it to be economically unprofitable, you basically know what to do by either overriding it to higher number, right? And so the next step for us to do is to load this up in our .env. And so let me just create a .env file, right? .env, and basically load all of this. So the next thing we want to do is to load the .env, right? As you can see, we have Polygon RPC URL and Aave to Polygon DAI, the rewards contract, the lender pool contract. And so because we're going to be forking um, Polygon mainnet, because this is where like all of the contracts we're using exist, we'll need all of these variables, hence why we have them in the .env. So the next thing to do is to test the votes. And to test our votes, we'll be doing two things. Like I mentioned, we'll fork the mainnet to verify like reward deposits and withdrawal flow. The next part is to do the standard conformance testing using A16Z property-based tests, right? And so for the first part, where we are going to be um, testing against the various functions, we'll test for deposit and withdraw, mint and redeem, and interaction with Aave V2 as like a yield source. So first part is to go over to this test file and then run this command. So everything exists in this code. All you have to do is just to go over them. So these are test contracts. As you can see, we have some addresses, some state variables, um, and also the setup basically. Um, Next part, it tests for each of the functions: single deposit, multi-deposit, in a case where one user deposits, and in a case where we have multiple deposits. Now, this basically tests for single deposit and withdraw at the same time, and then this tests for mint and redeem, and then this test for yield accrual after depositing. Then, as you can see, this basically simulates time passing over after like 365 days, right? And then we can check if it basically has yield accrued to it, right? So this is the essence of like the test flow, right? And to just see our testing practice, we can just run this code, and as you can see, the test is passing. And that's the first part for this. The next part is the standard conformance with ERC4626 test suite. Now let's go over the test suite from A16Z, right? But in any case, let's understand what this is doing. So beyond the functional testing that we did, it is critical to verify that the vaults adhere strictly to the ERC4626 specification. Now, this property-based test suite is maintained by A16Z. And what it does is that it allows vault developers to detect standard violation before deployment, and also integrators to validate third-party vaults before integrating them. To install the test suite, all you have to do is to copy this command and install, and then extend your test to use this implementation. But then let's quickly take a look at the repo itself and see what it has to say. So as you can see, this is like the repo. It says, what is this repo all about? It says it's a test suite for checking if the given ERC4626 implementation satisfies the standard requirement. I think that's the whole essence of this property test, to ensure that each vault satisfies the standard requirements, right, from the standard. And also, these tests are independent from implementation details, thus applicable for any ERC4626 vault. Adaptive style property-based tests for fuzzing or symbolic execution testing. Now, what this is not it does not test implementation detail specific, like how to generate and distribute yield or how to compute the share price. Now, the testing properties that will be tested for here is the round trip properties, meaning that no one can make free profit by depositing and immediately like withdrawing back and forth. Then it checks for like the functional correctness of each of the um, contract function as specified by the standard. The same thing for the preview, deposit, redeem, preview means withdraw, convert to shares and convert to assets, and every other function as specified by the standard. Now, one of the major things to note is that this property-based test is basically to ensure that every of your implementation, satisfies the standard requirements. That convert to shares must run down, right? And all of those, properties that has been specified by the standard. Now, having said that, the next thing we want to do is to write like a conformance test file, which we already did over here. As you can see, this is the conformance test file. So we have the mock version of all of the needed contract over here, to easily test for this property-based test, right? And so now we have the setup. It has the underlying assets, which is basically the asset controlled by the vaults, which is DAI, mock DAI, and the A token, which is mock A DAI, and every other contract that will be needed. Now, some of the variables to set for this property-based test by A16Z is thus. Now, let's have a look over here, right? Is the first part is the vault, which is like the address of ERC4626 vault, and then the underlying assets, right? Now, we are setting the vault because this is the vault is the contract that holds all of the function of the vault, and this is what we are testing against, right? That this vault conforms to the standard correctly. Now, the underlying asset is the asset managed by the vault, in this case, DAI, right? Now, let's talk about delta value. Now, in this case, if your vault implementation is perfect, right, you can set it to 0, meaning that it follows the specification. But if by any chance you have different implementation, you can, increase this delta value accordingly. As you can see, it says setting this to 0 indicates that the vault follows the preferred rounding direction maintained by the standard. Now let's talk about vault may be empty. It says that when false cases that empty the vaults are ignored. Now in this case, when set to true, we're basically saying that the property-based test should test for the scenario of vaults being empty, right? And in most cases, you know that empty vault has certain issues to deal with. Take for instance the first, depositor inflation attack. Now we also have the unlimited amount. When set to false, right? False inputs are limited to the caller's available balance and speeding up tests, but potentially missing some certain edge cases. Some of these properties are optional, and you can basically read about them over here. And then pretty much the next thing to do is to basically run like the conformance tests, right? And see, if it basically conforms with the standard. And so when we run the test, as you can see, tests for deposit, redeem, deposit, withdraw, mint, redeem, mint, withdraw, and everything passes, right? So this means that our implementation basically passes the A16Z property-based test. So that's pretty much about how to build a tokenized vault, how to test them, and if by any chance you also want to run the conformance-based test for them. We have now come to the end of this course. In this crash course, we covered the core building blocks of tokenized vault standard, and now you understand why vault exists, what is a vault, ERC4626 standard, the core technical specifications, the key security consideration with a focus on inflation attack, the different mitigation strategies for inflation attack, and how to build and test a vault implementation. You have also seen how to verify the correctness using the property-based testing from A16Z. Now, if you want to go deeper into ERC4626 and following ongoing development in this space, be sure to check out the Vault Foundation. Head over to Vault.Foundation, check out the different resources for Vault implementation, the various security considerations, and also guides. That'll be all for this course. Thank you very much for watching, and I'll see you in the next one.